Hey there. Today we're going to be looking at two topics. One is color mixing, and the other is going to be the law of reflection. Let's start with the color mixing. As we know, in the visible light, we have Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And you should know that the red is the longer wavelengths, blue are the higher frequencies, shorter wavelengths, and green is in the middle. Okay, we're going to be looking at additive, or the primary colors of light. We're not going to be dealing with here with pigments, or what we might refer to as subtracting. Okay, now when you see something that has white, white is not a color. White is all the colors together. And black is not all colors. Black is no colors, no light at all. Okay, so if something's black, there's no light. Okay, so when you see a black object, it is an object which, when light hits it, if white light hits it, all colors hit it, nothing is reflected, and you see it as black. If you look at a white sheet of paper and white light hits it, meaning all colors hit it, then all of those colors reflect and you see all of those colors. If you have a white piece of paper and only red light hits it, then you only see red light. It looks red, okay? But we look at something white, and the question is, why is it white? Okay, so now let's get into a little bit about the biology of this, because a lot of what we're going to deal with the primary colors of light, it's really not a physics thing. It's more of a human biology thing. In your eyes, we have cones, rods and cones. The cones deal with the colors, and so what you have is you have three types. You have one type of cone, which is more sensitive to long wavelengths. That would be the reds. Then you have another type of cone, which is better at detecting short wavelengths, the blues. And then you have something in the middle, and that would be the greens. And so really, your eyes are only really capable of detecting three types of wavelengths, ranges, short, medium, and long. We refer to them as red, blue, and green. Okay. Now, if you see something red, then really, when the red light comes in, only the red cones are being activated, and your brain sees that as red. If you are looking at blue light, only the blues are being activated. If you see green light, only the green is being activated. But how do you see something yellow? Well, when you see something yellow, when yellow light gets in your eyes, then what the yellow light does is it triggers the red a little bit and it triggers the green a little bit, because yellow is in between, and the spectrum is in between the red and the green. And therefore, when you see yellow, both the red and the green cones are being triggered. Your brain sees that as yellow. So now, there's two ways for you to see yellow. You can either have yellow light hit your eye and have it trigger the red and green both a little bit, your brain sees yellow, or you can actually be tricked to think you see yellow when you don't have any yellow light. And the way that would be is if green light came into your eye and red light, both green and red a little bit, and then those both triggering the red and green cones, and then your brain says, I've seen this before, that's yellow. And so there's actually two ways. And so we can actually see this here. If you look at what we've got is we've got a red section, a green section, and a blue section. Okay, so now what happens if we mix the red and green, you get yellow. That's not actually yellow there. Okay, in the intersection of that red circle and the green circle, it's still red and green. But when you look there, your eyes are being triggered by both the red and the green, and you will think you see yellow. Likewise, if we mix blue and green, we get a aqua, or might refer to it as cyan. Okay, if we do red and blue, we get what's often referred to as magenta. If you do all three of them, you'll get, in that intersection of all three sections, we get white. But the only colors that are present there are the red, blue, and green. Now this has great applications, especially with your computer screen and TV screens, because if you've ever gotten a drop, a real small drop of water on your computer screen or TV screen. In fact, you may want to try that right now on your computer screen. Put a small drop of water, and it acts like a lens, and it allows you to see the individual pixels on your computer screen or your TV screen. And then when you see white, you'll actually see red, blue, and green pixels all lit up. But if you were to put a small droplet where the yellow is, you'll realize there's no yellow there. There's just red and green. And at the cyan, there's blue and green. At the magenta, there's blue and red. So when you mix these, you're mixing these primary colors of light, but it's really not a physics thing. This is simply because you have red, blue, and green cones, sensitive cones in your eyes, and you can either see, for example, yellow light because yellow light hits you, or you can be deceived and you can think you're seeing yellow when really you're just seeing red and green. And that's how a lot of images that you get are really not what you think they are. They're simply tricking your brain. Now, these secondary colors are referred to, the yellow, the magenta, and the cyan are referred to as secondary colors. They are the mixtures of the primary colors. And if you mix those secondary colors together, of course, you get white as well. So we refer to the opposite colors. For example, the red is opposite the cyan. The red and the cyan are what are called complementary colors. And the blue and the yellow are complementary colors. And green and magenta are complementary colors. And you'll see, for example, if like we've talked about before, the sky is blue. Well, the light coming from the sun is pretty much got all the colors in there, so it's fairly close to white. But as it comes through the Earth's atmosphere, high frequency colors like blue are stripped away. So if we take white and subtract blue, we get yellow. So the sun looks yellowish here on Earth. If you go outside the Earth's atmosphere, it doesn't look nearly as yellow because more of that blue has been put back in there, has not been removed from it. The olden days when people take color photos of photographic film, the negatives are the complementary colors. So like if you were to stare at a particular color for a long period of time, say 30 seconds, and then look at a white sheet of paper and blink your eyes, you'll realize, oh, I'm seeing the complementary color of that color I was seeing. And so really what's going on there is often referred to that as kind of a retinal fatigue issue, although I don't think that's truly what's going on. What it is if you were to look at something red for a long period of time, your brain would get really good at ignoring the red. And then if you looked at something white, for a little bit of time, your brain would see all the colors, but it's still ignoring the red. And if you took white and ignored red, you would see cyan. The first computer screens that came out were monochromatic, meaning one color, and they were kind of a green color. And so you would have a lot of computer programmers who spent long hours every day looking at a green screen. And they found out that afterwards, when they looked at pieces of paper, they tended to look kind of pinkish, because that magenta is the complementary color to that. There are common optical illusions where you look at something. A real common one is an American flag that's the complementary colors, and you stare at it for a long period of time, say 30 seconds, and you look at a white sheet of paper, and then you actually see the actual colors of the American flag. That is a common thing there. So now, if we look at this little slider here, we can remove the red, and we notice that we get the cyan. It's all cyan. If we remove the green, that whole section is magenta. Remove the blue. So you can now mix varying amounts and get all sorts of different colors. Get all the different colors that you're used to seeing on a computer screen simply by mixing different amounts of red, blue, and green. Okay, those colors are not actually there, but your brain thinks that they're there simply for the fact that you've got the right amount of red, blue, and green that go together. Okay, so that's what we want you to know about color mixing. Now, let's take a look at the law of reflection. So law of reflection, when we do law of reflection, we're going to deal with plane mirrors. And so we have a mirror. And then we're going to have a ray that's going to come in, and the ray coming in is called the incident ray. And then we have this line called the normal. Okay, so the normal means perpendicular. It means perpendicular in a three-dimensional sense. Okay, and then what we get is we get the incoming ray and we get an outgoing ray. And the law of reflection simply states that the angle of incidence is equal to the angle of reflection. And these angles are always measured off of the normal. So this would be the angle of incidence, and this would be the angle of reflection. And those two angles are just equal. Okay, we see that to a certain extent if you play pool and billiards and you take a ball off a cushion, those two angles are pretty close to each other, but there's also friction that you can put on to deviate from there. But with light, it's right on. Okay, so we have the law of reflection, the angle of incidence equals the angle of reflection. And from that, you can simply you can predict a lot of things on what you will see. And you'll see that in some of the concept builders that we'll deal with. The key things that we simply want to know is got the mirror. The incident ray is the one coming in. The reflected ray is one going out. And this dotted line is called the normal. It is perpendicular to the mirror at the point where the incident ray strikes the mirror. So if the incident ray were striking at a different location, we would draw the normal at a different location. So in essence, there's an infinite number of normals. But the key is these angles are equal, but they're measured off of the normal. They're not measured off of the mirror itself. So hopefully that helps out.